In this video segment, we are going to look at how we can take the ideal gas law and apply it to a concept that we've learned previously, stoichiometry, or mole-to-mole relationships between reactants and products in a balanced equation. So let's remind ourselves about the ideal gas law. PV equals nRT, and a reminder that this law will enable us to calculate any one of the four variables that define a gas if we know the other three. So what that means, if you know the pressure, the volume, and the temperature of a gas, you can calculate moles of gas. And then once you know moles of gas, you can head right into a stoichiometry problem, exactly using the method and thinking of mass stoichiometry, where you take mass, convert to moles, and then move on into the stoichiometry calculation. So if we have a pressure, a volume, and a temperature, we can solve for moles of gas and then do a stoichiometry calculation. So there is nothing new to teach here. This is just an application of the ideal gas law to things that we have already learned. So let's take a look at a couple of example problems. The first, how many grams of potassium chlorate decomposed to produce 645 milliliters of oxygen gas at STP conditions? A reminder to you that in order to do any stoichiometry problem, and it should be clear that this is a stoichiometry problem, it's talking about a reaction, it's giving you information about oxygen, which happens to be a gas, so you are getting the volume and the temperature and the pressure of oxygen gas. From that, you can calculate moles of oxygen gas, and then the problem asks you information to find information about the reactant, in this instance, potassium chlorate. So this is a gas stoichiometry problem. We are going to take the volume, the temperature, pressure, solve for moles of oxygen, use a mole-to-mole relationship from the balanced equation to get moles of potassium chlorate, and then solve for grams of potassium chlorate. But we need that balanced equation. In order to get the mole-to-mole relationship, you need the balanced equation, and you should be able to write it for this reaction from the information given. Potassium chlorate is decomposing. That decomposition involves heat, and it is helped along by a catalyst, manganese 4 oxide. Remember that we write catalyst above the arrow. But the focus is on the product, oxygen gas. So writing the balanced equation for this reaction, we get 2 moles of potassium chlorate decomposed to give 3 moles of oxygen gas and 2 moles of potassium chloride. Taking the information that's provided and labeling it, a reminder to you that whenever you have a volume in milliliters involving the ideal gas law, it is necessary to convert that volume into liters, because the R unit for volume is in liters, and those units need to cancel. So I'm taking the 645 milliliters, dividing by 1,000, there are 1,000 milliliters in 1 liter, and converting that volume to 0.645 liters. STP conditions, 0 degrees Celsius, which is 273 Kelvin, and pressure in 1 atmosphere, we could have chosen 760. For this problem, I used the 1 atmosphere value. And from the pressure, temperature, and volume, we can calculate moles of oxygen. So let's go ahead and do that right over here. PV equals nRT. We need to calculate moles of oxygen. So dividing both sides of the equation by RT, we get number of moles of oxygen equals PV divided by RT. And of course, all of this referring to the pressure, volume, and temperature of oxygen, which we've labeled to the right. So coming down and doing the plug and chug portion of the calculation, where we plug in the data and calculate the value. 1 atmosphere of pressure, 0.645 liters. Remember, we don't want to stack our units, so I'm showing R written in its flipped, inverse, or reciprocal form so that the unit dimensional analysis will be clear and easy to look at. So dividing by R, which is multiplying by the inverse, and then sneaking our temperature in over here in the denominator where we have some space. Looking at the units and making sure that our dimensional analysis is working out. Our Kelvin is canceling, our atmosphere is canceling, our liters are canceling. Good thing we converted from milliliters to liters, and we have a mole unit in the numerator where it should be if we're solving for moles of oxygen. So taking our calculator out and just double checking that this calculation was done correctly. Dividing by 273, dividing by 0.0821, and I confirm that the result for this calculation is 0.0288 moles of oxygen gas. But the problem is asking us to solve for grams of potassium chlorate. Now we need to do the stoichiometry. And we recognize that the stoichiometry involves the mole-to-mole relationships from the balanced equation. Every stoichiometry problem has this ratio in its setup. 2 moles of potassium chlorate have to decompose to produce 3 moles of oxygen. So here is our mole amount of oxygen that was produced. We can come and take this mole amount, use that mole-to-mole relationship, and calculate moles of potassium chlorate, exactly as we learned in Chapter 7. Looking at the dimensional analysis, our moles of oxygen are canceling. We have moles of potassium chlorate, and then multiplying by the molar mass of potassium chlorate, we should get 2.35 grams of potassium chlorate. I don't know whether or not you recognized when you read this problem that because you are at STP conditions, there was an alternate method for solving this problem, a bit of a shortcut, that bypassed needing to actually go through the ideal gas law calculation. We could have used molar volume. So here I have an alternate setup for this problem where we take the volume of oxygen, which is at STP conditions, and we calculated and illustrated in a previous video that molar volume gives the relationship between the moles of gas and the volume occupied by that gas at STP conditions. Specifically, 22.4 liters is occupied by 1 mole of any gas at STP, and that value was calculated using the ideal gas law. So we can take the 0.645 liters of oxygen gas at STP and use our molar volume and calculate moles of oxygen. Then we go right into the rest of the stoichiometry problem. Once we have moles of oxygen, we use the mole-to-mole relationship from the balanced equation. 2 moles of potassium chlorate decompose for every 3 moles of oxygen produced. So our liters of oxygen are canceling, our moles of oxygen are canceling, and once we have moles of potassium chlorate, we use the molar mass to calculate our mass of potassium chlorate. And indeed, we get the exact same answer, 2.35 grams of potassium chlorate, using this shorter method. Again, STP conditions give you the option of working with the molar volume conversion factor. Let's do one more stoichiometry problem, this time a limiting reactant stoichiometry problem. And a reminder to you that all limiting reactant problems are signaled by you being provided information for at least two reactants involved in the chemical reaction. So let's take a look at this problem. How many liters of carbon dioxide gas at 815 torr and 37 degrees Celsius? So pausing here, we are not at STP conditions. So molar volume is not valid for use in this calculation because we are not at STP. So how many liters of carbon dioxide at this pressure and temperature will be produced by the reaction of 25 grams of propane with 80 grams of oxygen? And this is your signal that it is a limiting reactant problem. You're given quantities of more than one reactant. It is a stoichiometry problem. All stoichiometry problems start with a balanced equation. You should recognize that this is a combustion reaction because oxygen is one of the reactants. Propane is a fuel, a hydrocarbon fuel, burning in the presence of oxygen. So you should be able to write the balanced equation for this combustion reaction knowing that the products of all combustion reactions involving a carbon-based fuel, a hydrocarbon, are carbon dioxide and water. So writing the balanced equation for this reaction and then labeling the masses of each of the reactants indicated in the problem. 25 grams of propane reacting with 80 grams of oxygen. You are asked to solve for a volume of carbon dioxide in liters. You are told the pressure, you are told the temperature, so clearly we're going to have to solve for moles of CO2 produced in this combustion reaction. And if we have a pressure, a temperature, and a mole amount, we should be able to solve for our volume of CO2 in liters. How are we going to get that mole amount of CO2 produced? That's going to come from our limiting reactant comparison. How much CO2 will be produced from the 25 grams of propane? We can do a calculation. And how much CO2 will be produced from the 80 grams of oxygen. And I invite you to stop the video right now and do the calculation yourself, get your answer, and then join and see whether or not your work agrees with what we have here on the board, what I have written. So if you have done the calculation, then hopefully your setup looks like mine. Taking the 25 grams of propane, we're doing a comparison, asking how many moles of CO2 can be made from each one of these starting reactants. So taking our 25 grams of propane, using the molar mass of propane to convert to moles, and then looking at that mole-to-mole relationship from the balanced equation. Of course, we know there's an understood 1 in front of the propane. 3 moles of carbon dioxide gas is produced for every 1 mole of propane gas that reacts. So here is the heart of the stoichiometry problem, that mole-to-mole relationship. Now notice what I'm doing here. This is sometimes tricky for students when they're learning how to do gas stoichiometry problems. I need moles of carbon dioxide, not grams of carbon dioxide. So I'm going to stop the calculation right here with moles of CO2. I do not want to go to grams of CO2 because I do not need that for a gas law calculation. So stopping with moles of CO2 and doing this calculation, double checking, 25 divided by 44.1 times 3, I get 1.7 moles of CO2. But maybe oxygen is the limiting reactant. Maybe I can't make 1.7 moles of CO2 because I run out of oxygen first. So we have to show a comparison asking how much carbon dioxide in moles can be made from the 80 grams of oxygen. So here is that second stoichiometry calculation needed to make the comparison. I take the 80 grams of oxygen, divide by the molar mass of oxygen. Remember that oxygen is a diatomic molecule, so I need to add up 2 oxygen atoms to get the correct molar mass. And once I have moles of oxygen, I use that mole-to-mole relationship, which is the essence of the stoichiometry problem. 3 moles of CO2 is produced for every 5 moles of oxygen that reacts. And when I do this calculation, I get, hopefully, what I have written here, 1.5 moles of carbon dioxide gas. And now it's time to do the comparison. We remind ourselves that the limiting reactant is the one that makes the smaller mole amount of product. Comparing the 1.70 moles with the 1.50 moles, I see that the 1.50 moles of CO2 is the smaller amount. That means that oxygen is our limiting reactant. Oxygen is the limiting reactant and runs out first. So I can come over and put down the 1.50 moles of carbon dioxide is what is produced in this problem. I have a mole amount, a pressure, a temperature. I can use the ideal gas law to solve for volume. So here we go in the last part of the calculation. We have PV equals nRT. We're trying to solve for volume. So dividing both sides of the equation by P, we get the volume of CO2 equals nRT over P. And then it's time for our plug and chug. Plug in the values and solve for the variable. So I'm going to come in and put the 1.50 moles of carbon dioxide that we got from the limiting reactant stoichiometry comparison, filling in my R value. Because my pressure is in torr units, I need to use the 62.4 liters. Oh, and I'm double checking my work here, and I don't want a millimeter of mercury unit, I want a torr unit. So millimeter of mercury and torr are equivalent and interchangeable. So 62.4 liter torr per mole Kelvin times our temperature, which is 310 Kelvin. And notice I'm picking up that sig fig there with the decimal point, 310 with the decimal point. So I have moles RT divided by pressure of 815 torr. Looking at the units, torr is canceling, mole is canceling, Kelvin is canceling, and I am left with a volume unit of liters in the numerator, which is what I am trying to solve for. And just running through this calculation, and I hope that you are doing it as well. And I get 35.6 liters, which is the same number that I got when I did this calculation a moment ago before this video started. So I have confirmed with a double check the volume of CO2 produced in liters in this limiting reactant stoichiometry problem. Volume of CO2 is 35.6 liters.